Good morning, how are you? Today I want to take you on a lesson in chemical equilibria. So the first thing we want to look at is the concept of reversible reactions. Now reversible reactions are reactions which can occur in both the forward and reverse directions. We've got the forward reaction there whereby sulfur dioxide and oxygen are reacting to form sulfur trioxide. The reverse reaction is whereby the sulfur trioxide breaks down to give us sulfur dioxide and oxygen. If we're to represent those two reactions as one, we're going to use a reversible sign. Okay? Now, reversible reactions are written with a reversible sign to show that they can go in both the forward and the reverse direction. Now, all reversible reactions reach dynamic equilibrium. Now, for the reaction N2O4 gas reacting to form 2NO2 gas, we get a graph like this. Now, if you look at the orange line is showing how the concentration of NO2 is increasing. Now, NO2 is a product. So at the beginning of the reaction, the concentration of NO2 is 0. So it will rise up until a point whereby it stops rising. It stops rising at this point where there's a horizontal line. Now, for the reactant, the concentration of the reactant starts off at a maximum and then it decreases up to a certain point whereby it also becomes constant. Now, the point whereby the concentration of the product and the concentration of the reactant are constant is known as the equilibrium point. So the fact that these two concentrations are now constant shows that equilibrium has been achieved. Right. Now, dynamic equilibrium is described by two characteristics. Number one, at dynamic equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. We can see here that the blue line and the orange line, they are meeting at the same level here. So it's showing us that the rates are equal. The rate of the forward and backward reactions are equal. So that's one characteristic of dynamic equilibrium. Right. Now the second characteristic of dynamic equilibrium comes from the fact that at dynamic equilibrium, it might look as though the reaction is stopped because the concentration of the reactants and the concentration of the products will be constant, right? So this is the second characteristic of dynamic equilibrium. The concentrations of all the reactants and products are constant, but it does not mean that the reaction is stopped. The reaction is still continuing, right? But as soon as reactants react to form products, the products will also react to form the reactants. So it appears as though these quantities are not changing, but they are changing instantly, such that if you are to measure concentration at any particular point in time, it looks as though the reaction is stopped. There are no changes in concentration whatsoever. Now, the next thing we want to look at is Chatellier's principle. Chatellier's principle states that if a system in equilibrium is subjected to a change, processes which counteract the imposed change will occur. Now, the change can come in the form of temperature, concentration, pressure, or a catalyst. Amongst these changes, only temperature affects or changes the value of the equilibrium constant, which can be Kc if we're dealing with aqueous solutions, or Kp if we're dealing with partial pressures of gases. Now, how does temperature affect a reversible reaction? We can consider that reaction there whereby nitrogen and hydrogen are reacting to form ammonia. If you look at the enthalpy change of that reaction, you find that it has a negative sign notation. So we can conclude that the forward reaction is exothermic. And if the forward reaction is exothermic, it means that the reverse reaction is endothermic. So what happens if we increase temperature? If an increase in temperature is imposed, the backward endothermic reaction would be favored. Right? What would happen to equilibrium? Equilibrium will shift to the left as more products react to form reactants. Now, if a decrease in temperature is imposed, the forward exothermic reaction would be favored. Now, how does temperature affect a reversible reaction? You can take a look at that table there. It will show you how temperature affects a reversible reaction. Now, how does pressure affect a reversible reaction? Pressure only affects gaseous reactions. Now, this is a point that you need to take note of. Pressure only affects gaseous reactions. Now, pressure is inversely proportional to volume. Hence, when pressure increases, volume decreases. Similarly, when pressure decreases, volume increases. Now, since a reversible reaction can shift to the left or right, if volume changes, equilibrium can shift to the left or the right. But this only happens if the number of gaseous moles on both sides of the equation differ. Now, for the reaction N2 plus 3H2 forming 2NH3, there are 4 gas moles on the left and 2 gas moles on the right. Now, if pressure increases, volume would decrease, thus favoring the side with less gas moles. Hence, in this example, equilibrium will shift to the right, resulting in more products being formed. Now, if pressure decreases, volume would increase, thus favoring the side with more gas moles. Now, for this example, equilibrium will shift to the left, resulting in more reactants being formed. Now, if some of the reactants and products are not gases, their moles should be ignored. Now, you can look at that. You can look at these examples on how the position of equilibria can be affected by changes in pressure and thus changes in volume. Now, if you look at the first example there, we have 2 moles of gas on the left and 3 moles of gas on the right. Okay? And then for this example here, we've got 0 moles of gas on the left, and then we've got 0 moles of gas on the right. So such a reaction is not affected by pressure or volume changes. Now, we come here to the last example. We've got, how many of these? 3 moles of gas on the left and just 1 mole of gas on the right. Okay, so we ignore this here. This is not a gas. We ignore it. Now, how does concentration affect a reversible reaction? If you look at this example given there, we can deduce that if the concentration of H plus is increased, equilibrium will shift to the right and more products will be formed. Now, if the concentration of H plus decreases, equilibrium will shift to the left and more products will react to form reactants. Okay? Now, since the CrO4 2- is yellow and the Cr2O7 2- is orange, if equilibrium shifts to the right, the orange color is favored, whilst if it shifts to the left, the yellow color is favored. Now, how does the catalyst affect a reversible reaction? Now, catalysts can speed up the rate of both the forward and reverse reactions. They speed up these rates by the same magnitude. Okay. Now, this makes equilibrium to be reached faster. Now, a catalyst does not affect the position of equilibrium. Neither does it change the value of the equilibrium constant. Now, if we have a reaction like that, whereby A moles of A are reacting with B moles of B to form C moles of C and D moles of D, we can come up with the equilibrium expression as shown there. Right. Now, Kc is known as the equilibrium constant. Now, this C here shows us that K is in terms of concentration. Now, the square brackets there, these square brackets here, they stand for concentration of. So for this example here, the square brackets are telling us that we're looking at the concentration of C. Now we've got these smaller letters here, C, D, A, and B, which are raised as powers. Okay, now these here, they are coming from the balanced equation. Okay, so C there, this C, it's a number that we pick up from there. Okay, so if it's a 2 there, we'll come and put a 2 there. Right, okay? So you should remember also that the equilibrium constant in terms of concentration, we're going to use units of mole per dm minus 3, okay? We'll use units of mole per dm minus 3 for each concentration that we look at. Now, so for the reaction 2N2O5 forming 4NO2 plus O2, we can have a Kc expression as shown there. Look at this square brackets around NO2. And then look at this 4. Where is it coming from? We're picking it up here. The 4 is coming from there. And then we've got this 2 here. It comes and becomes the power there as well. Okay? So this is the Kc expression for this reaction. Right. Now, similarly, if we have a gaseous system like this one here, the Kp expression will be the partial pressure of C raised to the power of C times the partial pressure of D raised to the power of D divided by the partial pressure of A raised to the power of A times the partial pressure of B raised to the power of B. You can see that the C here is the capital letter. Now, the smaller c is also the stoichiometric coefficient. Unfortunately, here I did not put those smaller letters, but we can follow up from the previous example. Right. So this here shows us that for the reaction between hydrogen and iodine forming hydrogen iodide, we can have a Kp expression like this here after considering the balanced equation. Okay. We'll have a Kp expression like this. Right. So basically, if the partial pressure of hydrogen iodide is small and the partial pressures of hydrogen and iodine are small, we'll have a lower value for Kp. Okay. Basically, what I'm saying is that a lower value for Kp is telling us that the denominators will be larger than the numerator. Okay, the partial pressures of the denominators will be larger than the partial pressures of the numerators. Right, now it's also important for us to realize that the equilibrium constant of the forward reaction is the inverse of the equilibrium constant of the backward reaction. We can consider these two reactions here, N2O4 reacting to form 2NO2 and then 2NO2 reacting to form N2O4. You'll find that this Kc1 for this reaction is the inverse of Kc2. You can use these values and try and calculate using the calculator. You'll find that there's a mathematical relationship which can be shown using this equation. Okay? Right. Now there we have the summary of the conditions and how they affect the equilibrium position and the Kc. You can take a look at that later on. Now we have some questions here. You can pause and read that question. Right. And then you can look at the solution. Right. Now, initially we had 1 mole of this and 1 mole of that. We had 0 moles of this and 0 moles of that. After some time, X moles of this reacted and X moles of that reacted as well to form X moles of this and X moles of that. So here we need to subtract those X moles from the initial mole. And then we also subtract these X moles from that initial mole. And then here we're adding X moles and X moles, right? So there's a stoichiometric relationship here. 1 mole of this can react with 1 mole of that to form 1 mole of this and 1 mole of that. We need to understand this stoichiometry to come up with the initial moles and the equilibrium moles, okay? And then we also work out the Kc expression. We put the products, the concentrations of the products divided by the concentrations of the reactants, okay? So you have to understand that these equilibrium moles are not concentrations. In this example, we were not given volume, so we're going to divide by V. We'll divide the equilibrium moles by V so that we get the concentrations which we are going to substitute in these expressions. For example,